Welcome. There is nothing to do now but rest. Let your shoulders sink into whatever is holding you. Let your breath find its own unhurried rhythm. Tonight we drift toward the very edge of everything, back to a time before there was any space at all to drift through. You need only listen and let your eyes grow heavy. The universe is currently expanding. Every measurement astronomers have taken points to the same quiet truth. Space itself is stretching, carrying galaxies along with it. This is not galaxies flying through some fixed background, but the very fabric between them growing wider each moment. It happens everywhere, all at once, without any center. It is one of the most settled facts in all of cosmology. Galaxies are moving away from each other. From any galaxy you might stand in, every other galaxy appears to be retreating. Andromeda drifts from the Milky Way, and countless island universes drift from one another in turn. It feels almost like the surface of a rising loaf of bread, dotted with raisins, each one separating from its neighbors as the whole expands. No raisin is the center. No galaxy is either. The farther a galaxy, the faster it recedes. This simple relationship, distance tied to speed, was one of the great discoveries of the last century. A galaxy twice as far tends to be moving away twice as fast. It is a pattern so consistent that it reveals the expansion itself, written plainly across the depths of the sky for anyone patient enough to measure it. Edwin Hubble first measured cosmic expansion in 1929. Working at an observatory above Los Angeles, he compared the brightness and light of distant galaxies and found this same pattern of recession. His careful nights at the eyepiece, guiding a great telescope beneath a dark sky, quietly rewrote humanity's understanding of the universe's size and motion. Redshift reveals the velocity of distant galaxies. As a galaxy moves away, its light stretches toward longer, redder wavelengths, much like a sound lowering in pitch as it passes and fades. By measuring this subtle shift in starlight, astronomers can read a galaxy's speed from millions of light years away, translating color into motion, and motion into the story of an expanding universe. The universe is about 13.8 billion years old. That number, gathered from starlight, radiation, and the patient work of many instruments, marks the span since everything we can observe began. It is a span so long that human history is a single breath within it, and yet the universe still feels, in some sense, young in its unfolding. The observable universe spans roughly 93 billion light-years. This is the sphere of space whose light has had time to reach us, stretched wider by the universe's own expansion along the way. Beyond its edge, more universe almost certainly continues, simply too distant for its light to have arrived yet. We rest inside a bubble of the knowable, however vast that bubble is. Light from distant galaxies shows the universe's past. Because light travels at a fixed, finite speed, looking outward is the same as looking backward in time. The light entering a telescope tonight left some galaxies before our earliest ancestors ever stood upright on Earth. Every deep image of the sky is, in truth, an old photograph, arriving late. The cosmic microwave background fills all of space. It is a faint glow of radiation, reaching us from every direction in the sky, an afterglow left over from the universe's early, hot beginning. It surrounds everything we know, quietly, evenly, like a soft hush spread across the entire cosmos, present in the space between every star you have ever seen. Let your breath find its own slower measure now. There is no need to guide it, only to notice it lengthening, each exhale a little longer than the one before. Feel the air leave your chest, unhurried, like a tide pulling back from shore. With each release, let your shoulders sink further into whatever holds you. Breathing out is a small practice of letting go, and you are allowed to practice it again and again until sleep arrives on its own. The cosmic microwave background carries a temperature of about 2.7 degrees above absolute zero. This is barely warmer than the coldest possible state matter can reach, a whisper of heat spread across the entire sky. It began far hotter, but billions of years of expansion have stretched and cooled that ancient light. What reaches our instruments now is faint, low, and constant, like an ember that has been cooling since before the Earth existed. This radiation looks nearly the same, no matter which direction a telescope points. North, south, toward one horizon or its opposite, the glow arrives at almost identical temperature and intensity. Such evenness surprised early observers, who expected the young universe to look patchy and uneven. Instead, space itself seemed to have been smoothed, as though every corner of the sky had once shared the same breath of heat. Within that near-perfect smoothness lie tiny variations, differences of only a few parts in 100,000. Those small irregularities were enough. Regions slightly denser than their surroundings drew in more matter over time, slowly gathering gas under their own gravity. Across hundreds of millions of years, those faint differences grew into galaxies, and the galaxies into the great structures we now see scattered across the dark. That ancient light was released about 380,000 years after the Big Bang. On a cosmic scale, this counts as an early moment, though it followed an immense span of transformation already underway. Before this point, light could not travel freely at all. What we now detect is the very first light ever able to escape, carrying with it a memory of that instant, frozen and drifting ever since. Earlier still, the universe existed as an opaque plasma, a dense fog of charged particles through which light could not pass. Photons scattered endlessly off free electrons, bouncing from one to another without ever escaping in a straight line. If an observer had somehow existed then, the sky would have appeared as a uniform, blinding haze, bright everywhere and transparent nowhere. As the universe expanded and cooled, electrons finally joined with protons to form neutral atoms, and this shift is called recombination. Once electrons were bound into atoms, there were far fewer free charges left to scatter light. Photons, that had been trapped for hundreds of thousands of years, suddenly found open paths. That release is the very light we now call the cosmic microwave background, still traveling outward today. In the universe's first few minutes, nuclear reactions forged the very first hydrogen and helium nuclei. The conditions were briefly hot and dense enough to fuse simple particles together, much like the core of a star, but on the scale of all existing space at once. This process, called Big Bang nucleosynthesis, set the basic chemical recipe that later generations of stars would build upon. The proportion of helium found throughout the universe today closely matches what those early nuclear reactions predicted. Roughly 1/4 of ordinary matter by mass turns out to be helium, a ratio calculated decades ago and confirmed again and again through careful observation. This agreement between calculation and measurement stands as one of cosmology's quiet, steady confirmations, a number that simply keeps checking out. Alongside hydrogen and helium, the early universe also produced faint traces of lithium, though only in very small amounts. This lightest of metals formed in the same brief nuclear window before nucleosynthesis ended. Its scarcity and its precise measured abundance offers another thread connecting today's laboratories to conditions that existed only minutes after everything began. Carbon, oxygen, iron, gold, none of these existed in the universe's first minutes. Only the lightest elements formed then, hydrogen, helium, and a whisper of lithium. Everything heavier had to wait, sometimes billions of years, for the deep furnaces inside stars, and later the violence of stellar deaths to forge them. The iron in your blood, the calcium in your bones, arrived long after this early, simpler chemistry. Let your body grow heavy now, one part at a time. Feel your feet settle into the mattress, heavier than they were a moment ago. Let that heaviness climb slowly upward, into your calves, your knees, your thighs, each one sinking a little deeper. Your hips grow heavy, your back presses down, your shoulders lower, your arms grow full and still. Even your head feels weighted now, resting completely, asking nothing of you. Nothing living could survive the temperatures of the universe's earliest moments. Even the core of the sun, blazing at millions of degrees, would seem cold by comparison. In that first fraction of existence, temperatures soared past anything found inside any star, before or since. Matter itself could not yet hold together as atoms. Only as the universe expanded and stretched did things begin, slowly, to cool. Sound once moved through the early universe, though there was no ear to hear it. Pressure waves rippled through the hot plasma, compressing and releasing matter in rhythmic patterns. These are called baryon acoustic oscillations, and their fingerprints remain today, etched into how galaxies are spaced across the sky. Astronomers can still measure this ancient rhythm, a kind of frozen echo from a universe once filled with vibration. Before it stretched into galaxies and stars, the universe was smaller than a single atom. All of the matter and energy we now see spread across billions of light years was once compressed into a point too small to picture clearly, even in imagination. Physics strains at its edges, trying to describe such a state. What is certain is only that expansion, from that impossibly small beginning, never really stopped. The Big Bang was not an explosion happening inside space. It was the expansion of space itself, everywhere, all at once. There was no empty room waiting to be filled, no center point where a blast went off. Distances themselves were growing, carrying matter and energy along with them. This is a subtle but important distinction, one that reshapes how we should picture the universe's beginning. Galaxy surveys, spanning millions of light years, reveal something unexpected. Matter is not scattered randomly. Instead, galaxies cluster along vast filaments, forming a web-like structure with wide, nearly empty voids between the strands. This cosmic web resembles something almost organic, like foam or thread, though it was shaped purely by gravity acting over billions of years on matter both visible and unseen. No point in the universe holds a special claim to being its center. From any galaxy, in any direction, space appears to expand outward in the same way. This isn't a limitation of our instruments, it seems to be a genuine feature of the cosmos. Every observer, wherever they might stand among the stars, would see themselves at the apparent middle of an ever-widening universe. Whether the universe stretches on forever or curves back upon itself remains an open question. Current measurements suggest its geometry is remarkably flat, but flat does not necessarily mean unbounded. Cosmologists continue weighing models where space extends infinitely against models where it is finite yet vast, beyond ordinary comprehension. The evidence so far cannot fully settle which picture is true. Stars at the edges of galaxies move faster than visible matter alone can explain. This mismatch led astronomers to infer the presence of something unseen, something that adds mass and gravitational pull without emitting light. They call it dark matter. It cannot be observed directly, only felt through its influence on the motion of stars, gas, and galaxies swirling far from any galactic core. Something unseen is pushing the universe apart, faster with each passing age. Astronomers call it dark energy, though the name admits how little is truly known. It does not pull like gravity, it pushes, stretching the space between galaxies ever wider. Distant supernovae, used as cosmic mile markers, first revealed this quickening in the late 1990s. The expansion is not slowing down, as once expected. It is speeding up. Roughly 68% of everything in the universe takes the form of this dark energy. Ordinary stars, planets, and glowing gas make up only a small sliver of the whole. Dark matter accounts for more still, unseen but felt through gravity. Together, the visible universe, the one made of atoms and light, is almost a rounding error. Most of existence remains a quiet, unlit majority. Somewhere beyond these walls, a sound is settling, a low hum, perhaps a distant current of air, perhaps a house easing into the night. It rises just enough to notice, then fades again, like breath drawn and released. There is no need to name it. Let it come and go, the way tides visit a shore and withdraw without asking anything of the sand. The speed at which space stretches carries a name of its own, the Hubble constant. It tells you how quickly a galaxy recedes for every unit of distance between it and us. Named for the astronomer who first charted this motion, the number ties together distance and velocity across the cosmos. It is less a fixed truth than a measurement still being refined, generation after generation of telescopes. Depending on how it is measured, the Hubble constant comes out slightly different each time. Observations of the early universe's afterglow suggest one value. Measurements of nearby stars and galaxies suggest another, a touch higher. This small but persistent gap has become one of cosmology's quiet puzzles. Neither method appears wrong. Something more subtle may be misunderstood about the universe's expansion itself. Space itself, on the largest scales, appears remarkably flat. Not flat like a table, but flat in a geometric sense. Parallel lines stay parallel. Triangles behave as expected. Distances add up the way ordinary geometry predicts. Measurements of the early universe's afterglow support this flatness with striking precision. Curved universes, ones that fold back on themselves or flare outward, remain conceivable, but observation keeps pointing toward this planar shape. Such precise flatness is strange, almost too neat to happen by chance. For the universe to appear this balanced today, its early geometry would have needed extraordinary fine-tuning, unless something evened it out early on, a brief period of extremely rapid stretching, one that flattened any initial curvature, would explain the balance naturally. This idea, born from necessity, would later be called cosmic inflation. And look far enough in any direction, and the early universe's afterglow shows nearly identical temperatures everywhere. This is peculiar, because those distant regions, on opposite sides of the observable sky, were never close enough to exchange heat under ordinary physics. How did they end up so alike without ever touching? This puzzle earned a name, the horizon problem, a quiet contradiction sitting at the edge of the visible cosmos. A second puzzle sits alongside the first. Why does the universe balance so close to flat when countless other geometries were equally possible at the very beginning? A slightly different starting curvature would have sent the cosmos collapsing quickly or flying apart into near emptiness. Instead, it landed on this narrow, stable middle ground. Cosmologists named this quiet coincidence the flatness problem, and it demanded some deeper explanation. To answer both puzzles at once, physicists proposed something remarkable, a fleeting era of exponential growth just after the universe began. In this picture, space itself expanded so quickly that any early curvature was smoothed flat, and once distant regions were pulled apart from a shared, connected origin. This idea, cosmic inflation, offered a single, elegant explanation where two separate mysteries had stood before. Alan Guth, a physicist at the Massachusetts Institute of Technology, proposed a bold solution in 1980. He suggested that the universe underwent a brief, staggering burst of expansion just after its birth. This single idea addressed the flatness problem and the horizon problem in one stroke. Guth called it inflation, and the name has stayed with cosmology ever since. What began as a rough sketch reshaped how physicists imagine the universe's first moments. a fraction of a second. This is the sliver of time within which inflation is thought to have occurred. It began and ended before any atom could have formed, before light had a chance to travel any distance at all. Within that impossibly brief span, the universe is believed to have doubled in size again and again. Time, at this stage, moved through scales too small for ordinary intuition to hold, stretching tiny quantum fluctuations to enormous scales. Inflation is thought to have planted the seeds of everything we now see. Microscopic ripples in the fabric of the newborn universe were carried outward, magnified into vast differences in density. These small variations became the gravitational seeds around which galaxies, clusters, and voids would later gather. In this way, the largest structures in the cosmos may trace their origin to something smaller than a single particle. Let warmth begin somewhere small, perhaps behind your eyes or low in your chest, and let it spread from there. Feel it move into your shoulders, loosening what has gathered there through the day. Let it travel down through your arms, into your hands, until your fingers rest heavy and unclenched. Let it settle into your stomach, your hips, your thighs, sinking further with every breath. By the time it reaches your feet, there is only warmth and the dark and rest. The uniform glow of the cosmic microwave background finds its explanation within inflation. Regions that now lie on opposite sides of the sky were once close together, sharing the same temperature before being flung apart by the expansion. Inflation stretched that shared warmth across distances far greater than light could have crossed on its own. What looked impossible under ordinary physics becomes almost expected once this early stretching is taken into account. Inflation predicts something specific, a spectrum of fluctuations nearly identical across every scale of size. Whether ripples span the width of a galaxy cluster or something far smaller, their strength should differ only slightly from one another. Observations of the cosmic microwave background have measured this spectrum with remarkable precision. The pattern found matches what inflation anticipated, lending the theory some of its strongest support. Physics needed a name for whatever powered this expansion, and it settled on the inflaton field. This hypothetical field is imagined as filling the early universe, holding an enormous amount of energy briefly before releasing it. No particle linked to this field has ever been detected directly. It remains a theoretical placeholder, useful for calculation, but still unconfirmed by any experiment. Inflation may have ended through a process cosmologists call reheating. As the inflaton field's energy dropped, it is thought to have decayed into a shower of ordinary particles. This decay marked the boundary between the strange, stretching universe of inflation and the hot, dense universe familiar to standard cosmology. The transition, though brief, changed the character of everything that followed. In that instant, reheating is thought to have filled the newborn universe with a flood of hot particles. Radiation and elementary fragments poured into existence, raising the temperature far beyond anything measured on Earth today. This heat marks the beginning most descriptions of the Big Bang actually refer to. What came before, the stretching itself, left behind only its aftermath. No direct signal of inflation has yet been captured, yet the evidence surrounding it continues to accumulate. The flatness of space, the uniform temperature of the cosmic background, and the pattern of its ripples all align with what inflation predicts. Each observation adds a little more weight without offering final proof. The theory stands not on a single decisive test, but on many small, consistent agreements. Certain models of inflation predict a process with no true ending, known as eternal inflation. In this framework, expansion halts in some regions while continuing without pause in others, generating countless separate pockets of space. Each pocket may cool and settle into its own version of a universe, forever disconnected from its neighbors. The stretching, in this view, never fully stops. It simply moves elsewhere again and again without end. Inflation, under this idea, behaves less like a single burst and more like a restless surface, uneven and endlessly active across an unimaginable expanse. While some patches settle into ordinary space, still and complete, others keep stretching, forever generating new regions. Cosmologists call this eternal, not because it lasts within our universe, but because the process itself never exhausts itself elsewhere. Our observable cosmos may be only one settled patch among an unfathomable, ongoing froth. The Planck time marks a boundary within physics itself, a moment past which existing equations lose their meaning. It sits impossibly close to the universe's first instant, so early that no current theory can describe conditions before it. Physicists treat this threshold less as a wall and more as a horizon, beyond which our present understanding simply cannot see. Whatever happened there awaits a deeper framework not yet discovered. In ordinary units, the Planck time equals roughly 10 to the negative 43 seconds after the Big Bang. That span is so brief that comparing it to a single second resembles comparing a second to many times the current age of the universe. No clock, no process, no imaginable measurement could resolve anything happening faster than this. It stands as the smallest unit of time that physics can currently give meaning to. Let your attention rest on a single image, dust drifting through a shaft of light, catching gold for a moment before disappearing into shadow. Each speck moves without effort, carried by air too still to notice. No push, no pull, only drift, unhurried and complete. Let your own breathing take on that same unforced rhythm, rising and settling like specks of light finding their way down into rest. Before the Planck time, gravity and quantum mechanics must merge into a single description, though no one has yet written that description successfully. General relativity governs the large and smooth, quantum theory governs the small and probabilistic. At this scale, both are needed simultaneously, and neither framework alone suffices. The universe's very first instant seems to require a physics we have not yet built. Quantum gravity remains an unfinished chapter of physics, despite decades of dedicated effort. Multiple candidate frameworks exist, each attempting to reconcile the smoothness of spacetime with the graininess of quantum fields. None has yet produced a testable, universally accepted result. Until such a theory arrives, the universe's earliest moment stays just beyond the reach of confirmed science. At the Planck scale, general relativity begins producing numbers that no longer make physical sense, including infinities where finite values should appear. Einstein's equations, so reliable across galaxies and black holes, lose their footing at distances this small. The smooth curvature they describe seems to give way to a rougher structure, though no one yet knows its true shape. It's a sign that the theory, however elegant, is not the final word. Quantum field theory has explained nearly every particle interaction tested in laboratories, yet it treats spacetime as a fixed, unchanging background. In the earliest universe, spacetime itself was anything but fixed. It was part of what needed explaining. Without a way to let gravity bend and fields fluctuate together, the theory reaches a limit it cannot cross alone. A framework beyond both current theories seems necessary. The Planck length marks the smallest distance to which physics can currently assign clear meaning, far tinier than any particle ever observed. Below this scale, notions of position and separation seem to lose their usual sense, governed by rules not yet written. It is not merely small, it is a boundary past which our present concept of space may no longer apply. Many physicists suspect the answer lies in a deeper structure, still awaiting discovery. Space-time itself may become quantized at extremely small scales. Physicists suspect that the smooth continuum we experience might resolve near the Planck length into discrete units, like grains forming a beach. No instrument has confirmed this graininess yet. The idea recalls zooming into a photograph until individual pixels emerge from what once looked seamless. If true, the universe's fabric would have a smallest possible stitch, beneath which no further division makes sense. Intermediarities in Big Bang models signal the failure of current physics, not a literal point of infinite density. When equations predict infinite curvature or infinite temperature, cosmologists read this as a warning sign rather than a fact about nature. It means the mathematics has reached beyond where it can be trusted. Every known theory, pushed to that edge, breaks down in the same way. The singularity marks a boundary of ignorance, dressed as a number. A true singularity may not represent physical reality at all. It appears more likely an artifact of stretching an incomplete theory too far, the way dividing by zero produces nonsense rather than truth. Cosmologists increasingly suspect a deeper framework would replace that infinite point with a finite structured state, still unknown. The universe's true beginning, if it had one, may look nothing like the sharp edge the equations describe. Physicists debate whether time itself began at the Big Bang, or whether it simply changes character near that moment. Some equations allow time to fade smoothly into space rather than switching on abruptly. Others treat the beginning as a true edge, a first tick with no tick before it. No consensus exists, and the debate touches a deeper puzzle about what time actually is. Time, in certain frameworks, is treated as emergent rather than fundamental. Rather than a basic ingredient of reality, it might arise the way temperature arises from countless jostling molecules, absent at the smallest scale yet present at the larger one. If this view holds, asking what happened before time existed resembles asking about a single molecule's temperature. The question dissolves rather than answers. Notice the small muscles around your eyes and let them relax, one by one, starting with the corners you rarely think about. Let your jaw fall loose, tongue heavy, at the bottom of your mouth. The space behind your closed eyelids can feel wider than any room, dark and unmeasured, holding nothing that needs your attention. Each breath draws that inner darkness a little wider, a little deeper, until only the dark remains, and the slow rise and fall of breath, carrying you further from waking with each pass. Loop quantum gravity pictures spacetime as woven from tiny quantum threads, called loops, joined into vast interlocking networks. Rather than a smooth continuum, space would resemble chainmail at its most fundamental level, invisible at ordinary scales but granular underneath. Physicists working on this approach calculate that these loops carry a smallest possible area and volume. Nothing smaller than that unit of space is thought to exist. Inside loop quantum cosmology, the singularity disappears entirely, replaced by a quantum bounce instead. As density approaches the Planck scale, repulsive quantum effects are thought to overpower gravity's pull, halting collapse before it reaches infinity. The universe in this picture does not begin from nothing but rebounds from a prior contracting phase. What we call the Big Bang becomes a turning point rather than a starting line. A cosmic bounce theory suggests our universe emerged from the collapse of an earlier one, compressed nearly to nothing before rebounding outward. In these models, the story does not start with an explosion from emptiness, but continues an older story already underway. The collapsing universe would have grown denser and hotter, reaching some threshold before reversing course. What looks like a beginning may simply be a hinge. Bouncing cosmologies imply an infinite cycle of expansions and contractions, universe after universe, each rising from the ashes of the one before. There may be no first cycle and no final one, only an endless rhythm stretching in both directions. Cosmologists who favor this view describe time less as a line and more as a breathing pattern, contracting and expanding without end. Whether such a cycle ever truly began remains unresolved. Conformal cyclic cosmology imagines the universe repeating endlessly, each cycle ending in a way that becomes the start of the next. Roger Penrose, who developed this idea, suggested that when a universe stretches so far its structure loses all sense of scale, that infinite future can be mathematically stitched to a new beginning. Distance and time would fade into irrelevance, leaving only geometry to carry forward. The ending and the beginning become the same seam. Roger Penrose proposed that faint circular patterns within the cosmic microwave background might be scars left by a universe that came before ours. He and a colleague searched the sky maps for these rings, arguing they could mark ancient collisions from a prior cycle bleeding through. Cosmology has not confirmed the pattern beyond chance. The idea remains a hopeful thread, rather than settled ground. String theory suggests that reality carries more dimensions than the three of space, and one of time we notice around us. These extra dimensions, the theory proposes, might be curled so tightly that nothing at ordinary scale could ever detect them. Vibrating strings moving through this hidden geometry are thought to give rise to every particle we know. The shapes of those folded dimensions could shape the physical laws we live by. Within string theory, some versions describe reality as layered with membranes, vast sheets floating through higher dimensional space. A Big Bang, in this picture, could have been triggered when two such membranes drifted together and collided. The impact would have released tremendous energy, flooding the space between them with the matter and light that became our universe. Two neighboring worlds, brushing past each other, may have set everything into motion. The ekpyrotic model builds directly on that idea of colliding membranes, proposing our universe was born from such an impact rather than from inflation. In this account, two brains drawn together by an unseen force met, and their collision heated and filled the space between them with radiation and particles. The resulting expansion would look, from inside, exactly like our familiar Big Bang. Cosmologists still weigh this scenario against inflation's more established evidence. Neary attempts to gather the several competing versions of string theory into one unified framework, requiring 11 dimensions to make its mathematics consistent. Physicists developing this approach found that the different string theories, once thought separate, appeared to be different faces of a single deeper structure. 10 dimensions of space, plus 1 of time, would host membranes of varying sizes, some vast and some impossibly small. The full picture remains mathematical rather than something anyone has observed. Let your exhale grow a little longer than your inhale, and let it stay that way for a while. There is no rhythm to correct, only the one your body already knows how to keep. Each breath, drawn and gathers the evening around you. Each release lets a little more of the day fall away. Let the next exhale go on just slightly longer than the last, and rest inside that lengthening. A number of theoretical models propose that our entire universe formed inside the collapsing core of a black hole belonging to some larger, outer universe. As matter falls inward and crushes toward a singularity, the extreme density might trigger a rebound, opening into a new expanding space on the other side. From within, that new space would feel boundless, even as it remains tucked inside another world's collapsed star. Every black hole we observe, in this view, might be cradling a universe of its own. White hole models describe a theoretical mirror to the black hole, a structure that only ever releases matter and light, never pulling anything in. Physicists exploring this idea have wondered whether the earliest moments of our universe resembled a white hole flinging its contents outward, instead of a point exploding into empty space. No white hole has ever been observed, and general relativity's equations allow them mostly on paper. Still, the symmetry between falling in and pouring out is a pattern nature seems fond of repeating. Quantum tunneling models propose that entire universes can spontaneously appear from a state with no space, no time, and no matter at all, guided only by the probabilistic rules of quantum mechanics. Much like a particle that occasionally slips through a barrier it shouldn't be able to cross, a universe might tunnel into existence from sheer nothingness. The mathematics describing this borrows directly from laboratory quantum physics, scaled up to cosmic proportions. Existence, in this view, may not require a cause so much as a possibility waiting to be realized. In the 1980s, a physicist named Alexander Vilenkin proposed that our universe might have tunneled into existence from a false vacuum, a state that only appears stable while hiding deeper energy beneath its surface. No spark or explosion would be needed, only a shift allowed by quantum probability. A universe could emerge the way a particle sometimes appears where none should be. Existence, in this reading, resembles chance finding an opening rather than force breaking one. A false vacuum, once it begins to decay, could release pockets of lower energy that expand into universes of their own. Much like boiling water breaking into rising bubbles of steam, each pocket here becomes a nascent cosmos breaking free. Vilenkin's mathematics allowed such decay to happen repeatedly, scattered across some deeper, higher energy field. Our own universe, in this account, might be a single bubble among countless others still taking shape. Vacuum fluctuations may allow universes to appear probabilistically, the same way virtual particles flicker briefly into being within seemingly empty space. At scales too small to picture, energy borrows itself for the briefest interval before repaying the debt. Some theorists have asked whether, at a cosmic scale, such a fluctuation might instead unfold into a full universe rather than fade away. It would mean existence began as an accident too small at first to notice. Quantum cosmology models suggest the universe may have no unique beginning at all, no single moment that deserves the word start. Instead, the wave function describing all possible universes might spread across many configurations, with no sharp edge marking day one. Physicists working in this field describe existence less as a line and more as a landscape without a clear starting ridge. The question of a first moment may dissolve rather than ever being answered. Physicists James Hartle and Stephen Hawking introduced an idea called the no-boundary proposal, suggesting the universe has no edge in time, much as the surface of a sphere has no edge in space. Traveling toward the earliest moments would not lead to a wall, but to a smooth rounding, like walking toward a globe's pole and finding only more surface. There is no boundary to strike, only curvature continuing without a seam. The beginning in this proposal was never truly a beginning. Near the very origin, the no-boundary proposal treats time as gradually becoming space-like, losing its usual direction, the way a road might widen into an open field, with no single path forward. Ordinary time, with its past and future, would fade into a dimension behaving more like the three of space around us. Nothing marks the instant of transition, since the change unfolds continuously rather than at a hard line. What we call time may be a habit that space acquired later, appearing only once conditions allowed it. Certain models argue that asking what came before the Big Bang may be a question built on a false premise, akin to asking what lies north of the North Pole. If time itself emerged alongside the universe, then before becomes a word without a place to stand. The question feels natural only because our language assumes time stretches endlessly in both directions. Cosmology, in these models, suggests the question may quietly answer itself by dissolving. Notice now the weight of your body where it rests. Your shoulders have grown heavy against whatever holds them, and your arms have stopped asking to move. Let your legs feel the pull of the mattress beneath them. sinking a little further with each unhurried moment. Your head rests fully supported, no longer lifted by any small effort of your own. Let this heaviness spread from limb to limb, unhurried, until your whole body feels settled into stillness. Time itself may not have existed as a concept prior to the universe, since nothing was there yet to mark its passing. Without change, without motion, there would be no clock, no rhythm, no way to measure a duration. Physicists describing this stage often say that time did not stop before the universe, because stopping requires something already ticking. It may be closer to the truth that time began exactly where everything else did, inseparable from the rest of creation. Multiverse theories suggest our universe may be only one among countless others, each perhaps governed by its own laws and constants. Some arise from inflation that never fully ends, others from tunneling vacuums, still others from ideas not yet imagined. None of these other universes could ever be visited or observed directly, existing instead as a conclusion drawn from the mathematics that describes our own. Whether they are real or merely elegant possibility remains an open question. Eternal inflation, if true, could generate infinite bubble universes, each one blooming apart from an ever-expanding sea of energy that never stops producing them. Regions where inflation ends form pockets of ordinary space, cooling into something like our own cosmos. Elsewhere, inflation continues without pause, spawning new bubbles endlessly, forever. No edge would contain this process, no final count would ever close it. The word infinite here is not poetic license. It is the model's plain arithmetic. Each bubble universe within this framework might settle into different physical constants than our own, shaped by how the underlying field happened to cool as it broke away. One bubble's gravity could pull harder or softer. Another's electromagnetic force might follow entirely different arithmetic. The constants we take for granted here, the ones allowing atoms, stars, and slow-orbiting planets, may simply be the particular combination this one pocket landed on. The multiverse hypothesis remains, for now, untestable by direct observation, since no telescope can look past the edge of our own expanding pocket of space. Other universes, if they exist, sit beyond any signal that could reach us, beyond light, beyond gravity, beyond any known messenger. Cosmologists work instead with the mathematics that predicts them, hoping consistency and elegance stand in for evidence. Whether that is enough remains a genuinely open question within physics itself. Some physicists argue that multiverse theories, however elegant, are unfalsifiable, untestable in principle, not just in current practice. A theory that predicts endless unseen universes offers little for an experiment to disprove. Critics within the field suggest this pushes the idea toward philosophy rather than physics. Supporters answer that mathematics leading naturally to multiverses should not be discarded just because our instruments cannot yet follow where the equations point. The many worlds interpretation offers a different kind of multiplicity, suggesting that every quantum event branches reality into separate outcomes, each equally real. A particle deciding between two paths does not choose. Both paths occur, each carrying its own unfolding universe forward. Under this reading, countless versions of every moment exist side by side, invisible to one another, each proceeding as if it were the only one. Certain cosmologists propose something they call a landscape within string theory, not one possible universe, but a vast terrain of possible universes, each corresponding to a different way the theory's extra dimensions could curl and settle. Picture it less like a single valley and more like an entire mountain range of stable configurations, each valley a candidate for a universe with its own laws. Ours may simply be one valley among countless others in that terrain. The string landscape may contain something on the order of 10 to the 500 possible vacuum states, a number so large it exceeds any useful comparison, larger than the count of atoms in the observable universe many times over. Each vacuum state describes a different possible set of physical laws. Somewhere within that almost unthinkable range, our own universe's particular combination sits, one selection among a near-infinite catalog of alternatives. Anthropic reasoning offers one way to make sense of such a landscape. We observe a universe compatible with life, simply because only such a universe could contain anyone to do the observing. Under this reasoning, the question of why our constants seem so finely balanced dissolves somewhat, since any universe hostile to complexity would remain forever unwitnessed. It is less an explanation of the universe than an explanation of why we find ourselves inside this particular one. Somewhere beyond the walls, a low hum arrives and fades, the kind of sound houses make when everything else has gone still. It rises without hurry, holds for a moment, and lets go again, like breath moving through an old building. You do not need to name it or trace where it comes from. Let it pass through the room, the way it passes through the dark outside, arriving, lingering briefly, receding into whatever quiet waits beneath it. Your body can rest exactly where it already is. The fine-tuning problem asks a simple, patient question. Why do the universe's constants happen to allow complexity at all, rather than settling into any of the countless combinations that would produce nothing but sterile, structureless space? Adjust gravity's strength only slightly, and stars might never form. Shift the nuclear forces a fraction, and atoms heavier than hydrogen might never exist. The universe, as measured, seems to sit near a narrow set of values that permit stars, chemistry, and eventually quiet nights like this one. A statistical explanation for fine-tuning imagines countless universes, each carrying different constants scattered across some larger structure we cannot see. If enough universes exist, then a small fraction, perhaps one among an unimaginable number, would land by chance on values that allow stars, chemistry, and eventually life. Under this reasoning, our universe need not be special, only fortunate among a vast, mostly barren majority. It remains elegant and unconfirmed. Not every model of cosmic inflation requires a definite starting moment. Certain versions describe inflation as eternal in both directions, stretching backward without a true beginning, much as it stretches forward without a definite end. In such pictures, our observable universe becomes a small region within a field that may have always been unfolding. Whether this removes the question of a beginning or only relocates it remains unresolved. Whether time itself sits at the foundation of reality, or emerges from something deeper, divides the search for quantum gravity into several competing schools of thought. Some frameworks keep time as a basic ingredient, woven into the equations from the start. Others treat it as a derived quantity, arising only once enough underlying structure accumulates. Physics has not yet settled which picture, if either, is accurate. Causal set theory pictures space-time as built from an enormous scattering of discrete events, each connected to others only through cause and effect. There is no smooth continuous fabric underneath, only points and the causal links between them. Zoom out far enough, proponents argue, and this sparse causal network would resemble the familiar continuous space-time we experience. Zoom in, and only discreteness remains. Entanglement, in a growing body of theoretical work, may be the deeper substance from which space-time itself is woven. Particles linked through entanglement behave as though connected regardless of distance, and certain models suggest this connectivity gives rise to the geometry we call space. Remove the entanglement in these pictures, and distance would cease to hold meaning. Space, in this view, might be a consequence, not a container. A boundary far away, according to the holographic principle, might contain the complete information describing everything inside a given region of space. The three dimensions we move through could, in this view, be a kind of projection, arising from data encoded on a flatter surface at the edge. Nothing about daily life would feel different under such a picture. Only the deepest layer of description would change. Physicists have built a precise mathematical bridge linking a theory of gravity in a curved higher dimensional space to a quantum theory living on its lower dimensional edge. This correspondence, discovered in the late 1990s, gives researchers a rare working example of the holographic idea in action. It does not describe our exact universe, but it offers concrete proof that such a relationship between gravity and information can exist. Our universe, according to a small corner of physics speculation, might resemble something like a vast and intricate construct running on a substrate we cannot perceive from within it. Certain patterns in physical law, discreteness at small scales, apparent limits on information, mathematical elegance, are sometimes cited as suggestive, though never as proof. Nothing about daily experience would necessarily reveal such an arrangement either way. Despite its popularity in casual conversation, the simulation hypothesis remains a philosophical proposal rather than a scientific theory, since no experiment yet distinguishes a simulated universe from a natural one. It raises old questions dressed in modern language, questions about appearance, reality, and how either could ever be confirmed from inside a system. Cosmology continues to treat it as a curiosity at the edge of testable science. Let warmth begin at your feet, spreading upward gradual as sunlight settling into the blankets. Feel it reach your ankles, then your knees, loosening each muscle as it moves. It rises into your hips, your chest, unwinding whatever the day left behind. Let it climb through your shoulders, down your arms, into your fingertips, until warmth fills you completely and your whole body rests, heavy and unhurried, sinking into the dark. Many religious traditions describe a creator who exists outside time, untouched by beginning or end. In these accounts, the world unfolds from will rather than physical law, its origin folded into worship long before it entered philosophy or science. These stories differ widely across faiths, yet share one shape, something eternal standing outside the frame that would later hold planets, stars, and human wonder. Long before physics offered its own account, storytellers across the world imagined chaos as the first condition of everything. Formless, restless, without shape or direction, this chaos held the raw material from which order would later emerge. Greek myth called it chaos itself. Other traditions gave it different names, though the image recurred, a tangled beginning waiting to be sorted into sky, sea, and land. In ancient Babylon, priests told of a boundless watery abyss existing before the gods themselves. This primeval sea held no shore, no light, no separation between sky and earth. From its depths, according to the story, order was drawn forth, waters divided, heavens raised, the world given shape from what had been formless and dark. Hindu cosmology imagines existence as a vast, breathing cycle rather than a single fixed timeline. Universes rise, mature, and dissolve only to rise again, each cycle stretching across spans of time too immense for ordinary counting. Some texts describe this rhythm as the breath of a cosmic being, exhaling worlds into existence and inhaling them back into rest. Across indigenous traditions worldwide, many origin stories begin with a void, dark, waiting to be shaped by ancestral hands or spoken word. Some describe this emptiness as fertile rather than barren, already holding the potential for rivers, mountains, and living things. The shaping that follows is often gradual, an unfolding rather than a single dramatic act. Philosophers across centuries have asked whether true nothingness is even possible, or whether the very idea collapses under its own weight. Some argue that pure nothing, no space, no time, no potential, cannot be coherently imagined, since imagining it still requires a mind and a moment. Others hold that logic alone cannot settle the question, leaving it open across generations of thought. A number of thinkers propose that absolute nothingness, if it ever existed, would not remain nothing for long. Physical law, as we understand it, seems to resist perfect emptiness, favoring fluctuation over stillness. If nothing is inherently unstable, then something emerging from it might not require a cause in the ordinary sense, only the natural tendency of nothing to give way. Empty space, measured closely enough, turns out not to be empty at all. Quantum fields fill every corner of the vacuum, humming with fluctuations too small and brief for ordinary instruments to register directly. Even in the darkest, most isolated pocket of space, this quiet static of possibility persists, an underlying texture woven into the fabric of nothing itself. Inside that same vacuum, particles appear and vanish in pairs, borrowing existence for an instant before returning it. Physicists call them virtual particles, brief guests that never linger long enough to be directly observed, only inferred through their subtle effects on matter nearby. Their fleeting presence reveals a vacuum far busier than the word suggests, restless, energetic, and endlessly alive with possibility. A number of theorists propose that our universe began as one particular fluctuation, a chance ripple in a deeper vacuum that grew, through mechanisms not yet understood, into everything now observed. This idea remains speculative, resting on mathematics that stretches known physics to its very edge. It offers a striking possibility, that existence began not from divine will nor endless regress, but from the ordinary restlessness written into nothing itself. Somewhere unseen, a fire is losing its brightness, ember by ember, without hurry and without loss. Let your body follow that same slow fading, not going out, only settling into a dimmer glow. Your shoulders can loosen like coals losing their edge. Each breath draws the light a little lower, a little warmer, a little further from waking. Stephen Hawking once proposed a strange kind of time called imaginary time, where the sharp edge of a beginning could soften into something continuous. In this reframing, the universe's start resembles the way a curved surface has no starting point of its own, no place marked as first. Under ordinary time, the Big Bang appears to be a boundary. Under imaginary time, that boundary dissolves into a smooth, unbroken surface, as if the question of before simply stops applying. A cosmic beginning, in certain mathematical frameworks, may reflect the coordinates chosen rather than reality itself. Change the way time is measured near the earliest moments, and the sharp starting point can shift, blur, or even disappear from the equations. This does not prove the universe never began. It suggests instead that our sense of a definite first instant may be tangled up with the language we use to describe it. One model, known as the CFT-symmetric universe, proposes something almost mirrored, a second universe extending backward in time from the same central point, running in reverse, as though our cosmos were one half of a matched pair. In this picture, the Big Bang is less a beginning than a hinge, with time flowing outward in two directions at once. Neither half is more real than the other. Both simply unfold away from the same shared origin. Cosmological natural selection imagines universes evolving the way living things do, generation after generation. Each black hole, in this model, might spawn a new universe on its far side, inheriting slightly altered physical constants. Universes that produce more black holes would, over vast cosmic time, become more common than universes that produce fewer. It is a strange kind of inheritance, written not in genes, but in the values of nature's deepest numbers. Consciousness, oddly enough, appears in some corners of cosmological speculation, though this idea remains far from settled science. Certain interpretations of quantum mechanics assign a special role to observation, which has led a few theorists to wonder whether awareness might belong somewhere in the story of how reality takes form. Mainstream physics treats this as speculative at best, resting more on philosophy than experiment. The question nonetheless refuses to fully disappear. Philosophical idealism offers an older answer to similar questions, suggesting reality might be fundamentally mental rather than material. Under this view, matter, space, and even time could be expressions of mind, rather than mind being an accident of matter. Ancient and modern thinkers alike have returned to this idea, drawn by its strange elegance. It does not explain the physics of a cosmic beginning, but it reframes what beginning might even mean. Quantum mechanics, in certain interpretations, ties observation directly to the shape reality takes. Before measurement, a particle's properties can remain undetermined, existing as a spread of possibilities rather than a fixed fact. Only through interaction, some readings suggest, does one outcome become real among many. Physicists disagree sharply on what this truly means, and the debate remains far from resolved. Certain cosmological models propose that the Big Bang was not a single event, but many, scattered unevenly across an underlying expanse. In this picture, our observable universe would be just one bubble among countless others, each igniting at its own place and moment. These bubbles might never touch or communicate, separated by distances too vast for light to cross. What we call the beginning, then, may have happened more than once elsewhere and unseen. Chaotic inflation suggests that the stretching of space happened unevenly, more like weather than like a single uniform event. In some regions, inflation might end quickly, forming a universe like our own. In others, it could continue far longer, stretching space into shapes and scales beyond imagining. Across this uneven process, countless pockets could form, each with its own history, each unaware of the other's existence. Some theorists propose an infinite regress of causes before our universe, each cause born from an earlier one, stretching backward without end. In this picture, there is no first domino, no single spark that set everything moving. Causation simply extends into a past with no starting line. It is a vast, dizzying thought. Though it need not trouble you tonight, the chain, if it exists, has already carried you to this restful moment, unbothered by any need to trace it further. Let the jaw loosen now, unclenching by degrees, as though it too has somewhere warm to rest. The muscles around the eyes grow heavy, eyelids settling like a slow tide reaching shore. Behind those closed lids, only a soft darkness remains, wide, unmeasured, without edges. Nothing waits there, no shape to find, only the dark's easy hush, holding you the way night holds a field, long after the lamps have gone out. An infinite regress challenges the very notion of a first cause, the idea that something must have started the chain. If every event needs an earlier explanation, there may be no place philosophy or physics can point to and say, here, this is where it began. Some traditions find this unsettling, others find it strangely restful, a universe that never demanded a starting gun at all. Philosophers question whether causality itself even applies before time exists. Cause and effect assume a sequence, one moment following another in order. But if time has no meaning prior to the universe, the language of causes may fail outright to describe whatever came before, if before means anything at all in that condition. Eternal existence in certain models removes the need for a beginning altogether. Rather than starting at some definite point, the universe, or whatever underlies it, might have always been stretching backward without origin. Such models avoid the puzzle of a first moment by refusing to place one anywhere. It is less an answer than a different question, one that cosmologists find equally strange. A steady-state universe model offered one of the earliest alternatives to the Big Bang, developed in the mid-20th century. It proposed a cosmos with no beginning and no end, continuously creating new matter to keep its density constant even as it expanded. For a time, it stood as a serious rival, favored by physicists who found comfort in an eternal, unchanging cosmos rather than one born from a single fiery event. The steady-state model was abandoned after the discovery of the cosmic microwave background in the 1960s. That faint afterglow filling the sky in every direction was exactly what a hot, evolving universe would leave behind, and exactly what a truly steady, eternal one could not explain. Faced with this evidence, most cosmologists set the old model aside, and the Big Bang picture took its place. Some theorists propose that our universe is a fluctuation within a far larger metaspace, a fleeting ripple in something vaster than spacetime itself. Under this view, what we call the beginning may be only a local event, like a single wave rising briefly on an ocean too immense to picture. The rest of that ocean, if it exists, would lie forever beyond our instrument's reach. Metaspace, as a concept, would exist outside conventional spacetime altogether, not another place within our universe, but a condition prior to space and time both. Nothing in ordinary physics describes what such a space would be made of, or whether made of even applies there. It remains a name for an idea, a placeholder pointing towards something physics has not yet learned to picture. Physicists caution that we may lack the vocabulary to describe pre-space reality at all. Our words for before and after, inside and outside, were built for a world already furnished with space and time. Reaching past that furniture, language may run out of usable shapes. What lies beyond it, if anything, may need ideas we have not yet invented, spoken in a grammar we do not yet possess. Human language leans on space and time, even when speaking of things beyond both. We say a feeling is deep, a memory is behind us, an idea lies ahead. These metaphors work well for daily life, but they falter at the universe's edge, describing what came before the Big Bang forces words built for here and now to stretch toward a place they were never designed to reach. The phrase Big Bang was coined in 1949 by the astronomer Fred Hoyle, who used it half in jest. Hoyle favored a steady, eternal universe and meant the term as a mild jab at what he saw as an implausible explosion from nothing. The joke did not land the way he intended. The name stuck, outlived his objections, and became the everyday title for the very theory he spent his career resisting. Notice your breath, without trying to change it. In through the nose, low into the belly, and then a longer release out through slightly parted lips. Each exhale can run a little longer than the inhale before it, like a wave drawing back further than it came in. Let the next breath begin on its own, unhurried. There is no rhythm to get right, only the one already moving through you. Addressing the universe's origin may demand mathematics that has not yet been invented. Calculus once had to be built before gravity could be properly described, and quantum theory before atoms could be understood. Physicists studying the earliest moments now suspect the tools of geometry and probability, as they stand, may not be enough. A deeper origin may require a deeper language of numbers, one still waiting to be written. Quantum gravity remains one of the largest unsolved problems in physics. Gravity, described so elegantly by general relativity and quantum mechanics, which governs the smallest particles, have resisted every attempt to merge into one framework. Decades of effort have produced elegant candidates, but no confirmed theory. The two great pillars of modern physics still stand slightly apart, each true within its own domain, neither yet joined to the other. No experiment on Earth has come close to the energies of the Planck scale. The largest particle colliders reach only a tiny fraction of what would be needed, a gap so wide it is difficult to picture. Building a machine powerful enough to probe those conditions directly may lie far beyond current technology. Perhaps beyond any technology humanity will build in the foreseeable future. Future particle colliders may one day test small pieces of early universe theory, even without reaching Planck-scale energies directly. Certain predictions about particle behavior just after the Big Bang could leave traces detectable at slightly lower energies. Physicists design new machines partly with this hope in mind. Each generation of collider narrows the space where early universe ideas can still hide, without yet confirming or ruling any of them out. Gravitational wave observatories may eventually catch a faint signature left by cosmic inflation itself. Unlike light, gravitational waves could have traveled freely from the universe's very first instance, carrying information that photons never could. Current detectors are not yet sensitive enough to hear such a signal. Future instruments drifting quietly in space or buried deep underground may listen for ripples old enough to remember inflation directly. Gravitational waves from the universe's earliest moments, if ever detected, could offer direct evidence for inflation, where the cosmic microwave background shows only inflation's indirect fingerprints. These primordial waves would be a message sent straight from the event itself. No instrument has confirmed their presence yet. Finding them would mark one of the most significant discoveries in the history of cosmology, a signal older than starlight, older than atoms, older than nearly everything. Some physicists hope that future measurements of the cosmic microwave background's polarization will test inflationary models more precisely than ever before. A particular twisting pattern in that ancient light, if found, would strongly support the idea that space once stretched exponentially. Instruments sensitive enough to detect it are still being refined. The search continues patiently, one careful observation gathered after another, toward a pattern that may or may not be there. A theory of everything would join gravity with the quantum world in a single frame, and its pursuit still guides much of cosmology's daily work. Physicists chase it through equations, through experiments, through decades of careful failure and refinement. No such theory has arrived yet, though fragments of one seem to surface in unexpected corners of mathematics. The search itself has become a kind of quiet inheritance, passed from one generation of thinkers to the next. Cosmology remains an open frontier, its edges still unmapped despite a century of steady progress. Each answered question tends to open two more, quietly, without complaint. Researchers accept this as the ordinary shape of the work, not a failure of it. What began as scattered observations of drifting galaxies has grown into a discipline humble enough to admit how much still waits beyond its instruments. Asking what came before space may, in the end, have no answer that language or mathematics can hold. Time and cause seem to depend on a universe already existing to give them meaning. Outside that frame, the question might dissolve rather than resolve. Certain physicists have grown comfortable letting it remain open, treating the unanswered as its own kind of discovery rather than an absence. Let your body grow heavier now, one part at a time. Feel your feet settle first, sinking into the mattress like stones lowered into still water. Let that heaviness rise into your calves, your knees, your thighs, each one letting go a little more than the last. Your hips grow heavy, your back grows heavy. Your shoulders release downward, no longer holding anything up. Even your hands rest, full and unmoving, at your sides. Scientific humility means naming the edges of what we know without embarrassment. Every model of the universe carries assumptions that later observations might overturn, and cosmologists have learned to hold their theories loosely. This is not weakness in the field, but its quiet strength. A universe this vast was never going to be understood all at once, and admitting that has always been part of understanding it well. The mystery of where everything began still draws physicists and philosophers toward the same quiet horizon, each carrying different tools toward a shared wonder. Perhaps the universe had a single first moment. Perhaps it did not. Either way, you were shaped from the same ancient light and matter as every star overhead, part of the long, unfinished story of existence. Rest now, unhurried, beneath a sky that has always been patient with its secrets. Good night.